please give a wonderful warm welcome to an independent researcher working on human-centered AI, Sasha Mitz.
Okay, there we go. Thanks everybody for joining me today. We're going to be discussing the importance of what we'll refer to as calibrated mental models for building and making use of AI. The argument I'm going to put forward is that capabilities alone, new technology, is not enough. That in fact you need to couple a mental model to the capability to get sort of maximum leverage and positive outcomes. Okay, but before we talk about AI, we're going to talk about climbing a mountain, just as a sort of way to situate ourselves. So you can imagine that you and a friend are considering climbing a new mountain together. Maybe you've never gone up this route before. Maybe you can't see the path to the summit exactly, but you're going to sort of go for it. As you approach, you discuss maybe some ways you're going to go. Maybe you have different levels of aptitude or speed or confidence. You set up the rope that will join you together. If you've never gone rock climbing, you use ropes to ascend mountains safely with a partner. And as you begin, you might see something the other person has missed. You might propose one path that the other disagrees with. You discuss what you're going to do, and ultimately you make progress. We'll sort of refer back to this analogy a couple times throughout the talk. But you can imagine that these climbers, instead of just being climbers, are people representing the two parts that I discussed earlier, so the capabilities and the mental models. And the argument will be that these two need to work together to sort of most successfully ascend the mountain, and we'll discuss a bit what this looks like. Of course, AI is moving faster than many technologies in the past. We cannot just be sort of hopeful that this will go well. I'm going to argue that this needs to be deliberately constructed. Okay, the way we're going to break down mental models is into 3 layers. This is borrowed mostly from HCI literature, but adopted a little bit. The first layer is the system architecture, which concerns itself with how we expect the system to work. The second layer is the capability surface, which concerns itself with what does the system do and in what contexts. And then the final layer is what I'll refer to as the self-model layer, which is what can I verify and achieve given who I am and what I know, what I'm capable of doing. So to discuss this first layer, the system architecture layer, we're going to diagnose how users can be miscalibrated by today's AI experiences, largely because a lot of these experiences right now inherit a lot of anthropomorphic assumptions and don't ask users to engage critically with what is actually going on. I'm going to refer to this sort of first broader point as something called an interpretive gap. If you've spoken to a person before, I hope everyone here has, you may be familiar with the ways that conversations can go off the rails, but also we're quite good at recovering from that. You might notice that a person didn't hear what you said, or they weren't paying attention, or they had a different piece of information that you didn't realize they were making use of. But ultimately, because we have a shared cognitive architecture and social architecture, we can recover from those things quickly. AI does not have those things. It knows lots of information, but it makes very different kinds of mistakes. It can say things confidently, sort of irrespective of the level of certainty that it has. It can disproportionately weight past things in its context. And all of these things can be highly coherent and persuasive and encourage you to, or maybe even not encourage you, but subtly lead you to not take into account the fact that its fluency is not a stand-in for the actual certainty you ought to have in your conversation with it. You could imagine maybe as like a quick example, it says one thing, there's many paths that the system might take, and it's difficult for people to calibrate to the fact that they are having a conversation with a probability distribution. They're not having a conversation with a person who has some strong internal representation of what a coherent response is that they can actually execute on. Now, the inspiration for this talk was a bunch of things I imagine some of you have seen before, which are the disclaimers at the bottom of common chatbot windows. So you might see something like, can make mistakes, please verify its work, check what it says. And I want to sort of deconstruct these because I think there's a lot of sort of brittleness and unearned anthropomorphism going into this. So the first point, right, mistakes implies goal-directed deliberation, that the system has some intent in mind, which invites people to think of it the way they might think of a human collaborator. Asking someone to double-check responses presupposes that they have the verification capability that they probably don't have, right? Like you're using AI to augment you, to do work you maybe otherwise couldn't do or don't have time to do. And people are not calibrated to the way in which verification needs to proceed. And finally, the phrase is informed by telling. They're saying to someone, come to believe this thing, and then giving them evidence that for the most part contradicts that, because they're having this really fluent, convincing, high-quality interaction for the most part. Now, we'll talk a bit about the capability surface layer, so how deployment can change and strain as the sort of extent of the model's surface grows. We'll take a UX research example for sort of, I hope, obvious reasons, and go across sort of increasing levels of model capability. So at first, you might be working with just a conversational chatbot. You might ask it to do something like summarize a transcript, and you can give it feedback pretty routinely. But you can't exactly tell how past context is steering its results. On the sort of next layer, you could imagine a model that has a harness that includes some tools that it's able to use, and those tools might help you do things like analyze a whole batch of interviews. But you can only interact at the output media level. You can't see the tool interactions it's choosing necessarily, or you at least don't understand all the interdependencies between them. As we get to more agentic systems, you can imagine that the system is helping you with a synthesis of transcripts, but again, you're getting even further removed from being able to give high-frequency feedback, partially because it's just structurally precluded, partially because all of a sudden you're wasting time doing this. And a lot is hidden. So I've sort of tried to, at a very high level, illustrate this along the bottom of the slide. Now, you might say something like, well, it usually goes well when I use AI. It does lots of things. It saves me time. And of course, this is the case. If it didn't do that, we wouldn't be talking about it, right? We would just say, oh, well, it's a kind of useless technology, whatever. If you're don't have a good mental model for using it, that's fine. But I want to point out there's 3 cases in which things tend to hold, and then more and more these are not going to hold true, is my argument. So one, the task is in distribution, meaning it was sort of something the AI has learned to do in its training data, that the user can verify the output, and that the failures are recoverable. Now, if the task is in distribution, that's great, but more and more we're asking models to ensemble together lots of high-value things, which by definition are less common because there are multiplicative sort of stacking of things that it's done before. As we talked about already, verification is sometimes either structurally precluded or not a good use of people's time, or they may not have the mental model to be able to do verification work. And as we ask AI to do more and more work that is taking action in the world rather than just providing us some documents, failures are not recoverable, because when you book a flight or buy a cake, those are actual things that have happened that are not just documents that it's created on your computer. OK, so we'll talk more about sort of how these unpack, but I want to point at a high level that the things that we need are confidence and goal alignment, in process integrity, bounded expectation about failure. These are all things that having a strong mental model of a system helps you to do, and things where not having it leads to sort of what we can call inappropriate reliance or uncalibrated trust. So we'll spend some time now discussing the self model. We'll return to the climber analogy, and you can imagine that what I've been discussing so far could be characterized as in 3 different ways. So one, potentially the climbers are coupled, they're working with one another, they're ascending the mountain collaboratively, and they're pointing out ways to make progress. This is not going to happen by accident. It requires deliberate attention to what the other person is doing. In the sort of coupled but uncoordinated case, the 2 climbers are still attached to each other, but they may be pulling in different directions. They may have different ideas of how to ascend the mountain. And finally, you might imagine that there's some totally uncoupled situation where the 2 climbers are just climbing up the mountain together, somewhat unsafely. They're sort of taking things as they like. But we're going to consider a few historical cases to help us figure out how to stay in this more coupled, coordinated paradigm and away from the other 2. So I think this is a fun example. We talk a lot about things in modern technology, but this is an example that is a bit more historical. So the thermometer, we think about this every day. We use thermometers to tell whether we're sick or not. Obviously, at some point in history, that wasn't true. And when did it happen? So in 1612, the first thermometer was invented. Liquid goes up and down in a tube. It gives you some information. But it took over 250 years before that saw widespread adoption in the medical industry. The reason for this was not that the thermometer didn't exist. It was that people had no idea how to make sense of those numbers and apply them to their lives. So there 2 things happened a year apart that were critical. One was a thermometer that could retain the top temperature measured. So it would basically lock the fluid in place so you could see what was the maximum reading. And then another physician collected over 1 million measurements and developed a standardized understanding of how temperature correlated with disease state. Those 2 things together shifted the practice such that thermometers became commonly used across all of medicine. Every doctor's office I'm sure you've ever been to has taken your temperature, and that is a direct result of this work. What these people were doing were acting as bridge users They were understanding current practice, imagining a potential future state, and doing the work to couple the new technology to a mental model that took into account what was currently possible and what was now possible that was new. So let's consider one other example that are on a different topic, but I think are a nice pair for each other, which are expert systems and early aviation. Both struggled with something that we'll refer to as basically a non-uniform reliability. So they work sometimes and they don't work other times. The issue with expert systems is that that inconsistency was completely opaque. Basically, they make some prediction, but you as a user don't know when it's going to fail. In the case of early planes, this was similar, where there was inconsistent performance when the planes were flying. Maybe there were engine failures. But what they were able to do was create standardized instrumentation that effectively took early pilots' sort of hard-earned expertise and externalized it so that people could learn from it and take actions on it. Planes could be engineered to be more robust, given instrumentation that tells them things like altitude and wind speed and shear and all these other things. We have planes today. We don't use expert systems that much. Now, I want to touch briefly on a few papers in this domain. I want to point out these are early papers, mostly because this is a rapidly evolving field, but they all build on sort of a literature in HCI and trust and automation that point out three converging themes: that with sustained use, there is a substantial risk of degradation of human capability and skill for a couple different reasons. So one, that sustained dependence can basically cause people to have a collapse of their ability to return to like some baseline skill level. This was computationally modeled, so this is not empirically proven in people, but that reserving some small percentage of work can help to repair. In a second case, there's an argument that interpretive authority can be rapidly delegated away and that there needs to be some externalized governance model. And then in the final case, that human oversight can become completely nominal and sort of a rubber stamp when the volume of AI outputs becomes too great. It basically becomes the case that people can't keep up, but they still want to sort of feel involved, and they just push things through without having a robust internal representation of actually what's going on. So again, like, these converge on a concern. They diverge on what the resolution is. I think actually a lot of the work that remains for us and for other folks in sort of adjacent fields is to empirically verify and prove out in which cases which of these solutions are appropriate to apply. Now, I want to provide everybody, this is like, maybe somewhat stressful to hear all the ways in which things are like not exactly going right, with some principles we can apply to do this coupling work between mental models and capabilities. So I'm not going to try to read everything to you guys, but I want to touch on a few of these points. So one we mentioned, which is to make the operational boundary legible, to make clear what signals exist about where the system is in its operational space and how do we make that available to our users. Make clear sort of what is system understanding and what is system trust. A system might understand something. It doesn't mean necessarily that you should trust it. That the capability surface has to match affordances to the system's properties. Chatbots today, I would argue, do not do a good job of this. That you need to track the conditions that you are leaning on to substantiate your trust, whether these are verifiability or recoverability or others. And you need to build a self-model that cultivates domain-specific knowledge and also keep unaided baseline work alive so that you can not fall into this sort of detached pit that you can't recover from. Now, that might even still feel slightly too abstract, so I put together a set of sort of things that you can do on Monday, or hopefully you're not going back to work tomorrow, you're staying at Learners, but if you are, maybe you can try these things tomorrow. And I broke these again across the different mental model layers. So things like periodically testing what your assumptions are and where the system is relative to the edge that you believe. Notice when fluency outpaces your ability to evaluate. Conduct manual verification where you have expertise. Log the surprises that you encounter. Make unaided baseline work part of your practice. And propose sort of new methods and ways of understanding and share these with the field. So, we can imagine that sort of UX research example that we took on the earlier slide of sort of when we were talking about increasing levels of agent autonomy. Maybe some things that could be applied in that case are work on boundary legibility. So making clear when the system is performing in a way that is that is sort of well supported by data versus just interpolated from what it's learned in training. Match the affordances of the research tooling that you're building to what the model can actually support. So creating basically contracts with the system where it is forced to encode its responses tied to some evidentiary standard or to flag its uncertainty. And finally, learn from experts or become the experts yourself in a given field. What are the right criteria for applying these tools relative to what you're expecting them to deliver for you? Now, I just want to close by making a few points sort of to reiterate, right? Like the frontier is moving. We're not going to get there, this is my opinion, with capability alone. We need calibrated mental models that will help us make sense of, see broad adoption of things that we build, and also help us and our users imagine how things could actually be different. The work is multidisciplinary. I think user research has a compelling role to play here, but it relies also on alignment research, safety research, HCI, design, engineering, all these other fields. But we do have experience studying situated use, eliciting tacit knowledge, turning field observations into practice. But the operational states ultimately need to be surfaced transparently. That we need to be relying on appropriate paradigms, and we need to seek representation in building coupling. So I just want to close with a question. What can more calibrated mental models look like? How can we enable a next generation of AI experiences that leans on deliberately building mental models and bridging them to the capabilities we see and we want to see to make better things for ourselves, for our users, and hopefully for the broader world. So thank you, everybody, and hopefully we have time for a couple of questions. We'll see.
Let's take one question. Anybody want to ask a question? See a hand there, right there.
Hey, thanks for the chat. I'm curious about your thoughts on calibrating trust in these systems. You talked a lot about calibrating mental models. Yeah. Thinking about these unrecoverable errors that you touched on, when they inevitably do happen, how can we ensure that trust is regained after a real-world consequential error?
Yeah, so I think there's also a lot of, at least some research already that shows that trust is easier to lose than it is to regain. So I think this is a really important question, because if you lose it, then the question is like, yeah, maybe how do you get it back, or how do we recover? I think something that systems are getting slowly better at is addressing their relative level of confidence, but usually only when asked, not always. So that is maybe one area where we can encourage sort of model outputs to more systematically represent their level of certainty and the reasons for their level of certainty, and also scaffold users to better be able to vet and interpret the decisions they're making. Ultimately, these are things that are somewhat structurally precluded, from my sort of opinion and understanding of current model architectures, where they're not pulling on facts about the world and then asserting conclusions from those facts. They are probabilistically predicting sequences of words. So to do a really good job of this might require either substantially more scaffolding than current models have in this direction, or just entirely different training paradigms. I'm not an expert in transformer training or NLP, so I want to be a little cautious about stating what has to be done. I think there's ways we can nudge models, but I'm not convinced we can get there all the way with the current architectures.
Yay. Thanks, Sasha.
Yeah.
Give it up for Sasha, everybody.